Hey, welcome back to Fan Mama Physics. In this video, I'm going to do example 7 in 6.2 part 1. And this has to do with gravitational field strength. The diagram shows a planet near two stars. Okay, so I probably need to erase a few things so you can kind of see where everything is. So notice my planet is over here, and I'm just going to erase a few things. Okay, so that each star has a mass of 2.0 times 10 to the power of 30 kilograms. So these guys over here are very massive. Their centers are separated by a distance of... The number here does not match the number up here. So I'm going to assume this is, it's supposed to say 6.8 times 10 to the power of 11 meters based on the diagram. The planet is at a distance of 6 times 10 to the power 11 from each star. Okay, so it's kind of halfway in between both of them. And this is 6.0 times 10 to the power 11 meters from each star. Calculate the magnitude and state the direction of the resultant gravitational field strength at the position of the planet. Oof, oof. Well then. This is a very classic, what IB would give you as a problem. So we need to break it down first. We know it's vector addition, so we might as well draw the vectors in first. Now, this planet is going to experience a gravitational field, a gravitational pull from this star here on the left. So he's going to get, let me draw this bigger so I have space to work with, okay? So that is one of them. So I'm going to write G here. And G is going to be the same for both stars since they're both the same distance away. And the two stars are exactly the same. So there is, we also have the same gravitational field, the vector from the other star over here. Okay, so they're the same G value. Not that I did a great job drawing it out. But essentially, if since the planet is smack in between the two, notice that if I labeled the two axes, the x and y axes here, notice that my two horizontal axes are going to cancel out because the two planets, the two stars are equal distance away, and the planet is smack in the middle. Which means what we really care about is the vertical component of both g's. So I'll call that gy, and I'm going to also get another gy from the other star as well. Okay, so the idea here now is to find the gy component. To find the gy component, we need to know this angle over here. Okay, this angle over here is going to tell us the component that we need to get. To find that component, or to find that angle, we need to look at this as a right triangle. So I'm gonna divide the triangle in half, in which we have a right triangle here, and the base is going to be half of 6.8, which is going to be 3.4 times 10 to the power 11 meters. I have the hypotenuse, I have one side, I can use that to figure out that angle up there. So let's do that. So this angle is going to be sine theta of the two ratios. So sine theta, I'm doing it down here by the way, is going to be the 3.4. And since it's the same order of magnitude, I'm just going to do 3.4 divided by 6, okay? And the angle is going to, that I'm going to take the inverse sine of the two. And that's going to give me 34.5 degrees. And I'm going to save this angle later because I'm going to need it for finding the component of the gravity, okay? So now that we have the setup, we need to find the direction. Oh, direction, wait. Magnitude and state the direction. Okay, well then. We know that because there are two stars, we're going to get two GYs. Okay? And we know the GXs are just going to cancel out because you get one opposing the other one. So the net resultant gravitational field strength is going to be 2 times gy. And we know that gy is going to be g times the y component, which is going to be cosine of theta. Cosine of theta we know is 34.5. We just found that out a little while ago. And the last but not least is we need to figure out what g is. Gravitational field strength is due to the star. It's going to be equal to... here, let me just put in the cosine of 34.5 first. Okay, and so g is going to be big G, gravitational constant. The mass of the star, which is pretty big, 2 times 10 to the power of 30. I think that's the size of the sun. Okay, and then the radius, or the distance away, which we're given, is 6.0 times 10 to the power of 11. And don't forget this is squared, okay? Because don't forget to find gravitational field strength. Let me write it down here, is equal to big G times big M over R squared, okay? So we just calculate this all out. Don't forget G is 6.67 times 10 to the power of 11, or negative 11, sorry. Okay, so let's do this. I get... this is 6.1, and even rounded to what? 2 sig figs is just 6.1 times 10 to the power of negative 4. And this is a gravitational field strength, so this is going to be Newton per kilogram. And don't forget, we also need a direction. Direction is going to be, does it say any relative direction? No. In that case, I would put towards the stars, towards the midpoint of the two stars. Okay. And of course, if you label this as south, sure, you can do that as well. But really, in outer space, there is technically no north, south, east, west. Everything is all relative, so there's no absoluteness in that case. So relative to the stars, or towards the midpoint of the two stars, work just fine. Okay, well then. Phew. So notice that 2D vectors are coming back to bite you if you don't remember how to do those. So that's the essence of doing working with vectors, adding up the sums. So I thank you for watching. Hopefully you learned something. Good luck. Fan Mama Physics signing out.